Hi everyone, my name is Teja and welcome to this video series on probability refresher for business analytics and machine learning. So in this video, we're going to introduce another concept, which is expectation of a random variable. Okay. So before I jump into that, remember, I think in the past couple of videos, I was talking about discrete random variables. And I said there is also continuous random variables, and the only distinction is that discrete random variables take they take random variables are functions, so they take outcomes or elements of the sample space as inputs, and they evaluate them to values which are discrete in the discrete random variable case. For example, some um, finite collection of numbers, and in this case the random variable can take a real values like minus 1.1, maybe any value between minus infinity to infinity, for example. So this is just an example, whereas here it could be just 10, 20, and 30, right? So that's the only distinction, and there are some distinctions. As I was saying last time, there is a little bit of need for calculus here, but I'm gonna in this video, as well as I think a couple of more videos, I'm gonna stick with discrete random variables while defining things like expectations. Okay, so what is expectation? So an expectation intuitively is just a way to think of a, it's a property, okay, that I can ascribe to a random variable. And what is this property? It's a property that should be interpreted as um, an average, actually. So what is an average here? Okay, it's the average if you remember x is a random variable. Let's say it's the random variable, and it is attached to a sample space which has a bunch of outcomes. So let's say and you can think of each sample space and outcome as like an experiment. And so conducting an experiment would give me an outcome, right, with some probability. So that was my belief that that outcome would realize. But when maybe I run the experiment and I got an outcome. So if I run that experiment, hypothetically, if I run that experiment maybe 100 times, 1,000 times, I get different outcomes, right? So I can map those outcomes to numbers using this random variable, which is just a function from outcomes to numbers. So I'll get a bunch of um, values here. I can take their average, okay? So that average is called the expectations. That's just a way to interpret what the expectation means. It's a number which is like which tells us some information about the random variable as well as the probability law governing the sample space. Okay, so what is the formal definition of the expectation? For discrete random variables, it's simple. It's notated using the square brackets and the symbol, I mean E letter, and it's going to be just the summation of all the values that the random variable can take. So all the values, let's say little x, that the random variable can take, uh, summation of little x times the probability that the random variable takes the value little x. Okay, so this one we saw just before. So the expectation is simply the values that the random variable can take times the belief that the random variable will take that value. You sum this over all the values that the random variables can take. So for example, last time I said 10, 20, and 30, and the probability mass function was 1/3, 1/3, and 1/3, right, for each of these values. Then the expectation is nothing but, in that case, would be 1/3, um, sorry, 10 times 1/3 plus 20 times 1/3 plus 30 times 1/3. Okay, which is what? It's 60 by 3, which is 20. Okay, in this case, the expectation of this random variable, this uniform random variable, uniform discrete random variable, is 20. Okay. In general, um, So not in general. So let me, yeah. So let me now jump to an example, which is the Bernoulli random variable. So this one we saw last time as well. So which is x, which takes a value, let's say 1, with probability. I think last time I used 0.3, and 0 with probability 0.7. Then what is its expectation? It's easy to see. Expectation of x is 1 times uh, 1 times 0.3 plus 0 times 0.7, which is equal to 0.3. Okay, so it's just this guy. So this is an easy computation. In general, think of our sample space, right? And think of an event A, which is a subset of the sample space, right? So our sample space is some box, and there's an event A. This is the event A here. Okay. So what if I define? So A is a um, bunch of outcomes in the sample space, right? Which may have some property, right? I mean, I can just define this collection of outcomes as outcomes in the sample space, but may have some additional properties, right? So that's such that A is a nice, interesting event to investigate. Now I can define a corresponding random variable x, which is going to be a function, and this function is going to be the indicator function. So what do I mean by that? So this function is going to be indicator. What's a good notation for this? Um, uh, okay, so let me just use indicator of A. So what is this? This is like just a boldface 1. Okay, I'm going to use this boldface 1 and A. So this is an indicator of A, which just means that x takes a value 1 if um, omega belongs to A, right? And x takes a value 0 otherwise. And we know that omega belongs to A with probability P of A, right? So A is those omegas, is a subset of the sample space. So uh, the probability, the belief about event A happening is P of A. So x taking a value 1 is also with P of A, right? And x taking value 0 is 1 minus P of A. Okay. So then for this random variable x, expectation of x is just P of A. Okay, it's 1 times P of A plus 0 times 1 minus P of A, which just turns out to be P of A. Okay. So this is an interesting connection to Bernoulli. So this is just, I gave you this example to just expand your horizon, to think of, okay, not just Bernoulli where everything is nice and well defined, but also if there is an arbitrary event A, and if somebody defined a random variable, which is like, okay, this random variable is gonna take, if the outcome is in A, it's going to evaluate to 1. The outcome is not in A, then it's going to evaluate to 0. Then that random variable, its expectation is nothing but the probability of event A itself. Okay. Um, okay. So that's a couple of examples for expectation. Now I'll just describe a couple of properties. First one, so 3 properties. So what is the first one? So I said x is a random variable is just a function. I don't know. Yeah, a random variable is a function. So um, from omega to, let's say, some set of numbers, I can maybe some of you have seen this before. There is this notion of a composition of functions. It just means that, okay, there's some initial bunch of maybe numbers. Maybe the first function, I'm going to use f1 to denote that function, gives, given any number here, maybe 10, it may be, maybe 10 whatever, some numbers, maps to some other bunch of numbers. Maybe here it's um, everything divided by 10, so maybe 10 becomes 1 or something. Then another function, f2, can take these numbers and produce another output, maybe squares of them. Maybe 1 just remains 1, but maybe if there's a 2 here, it becomes 4, and so on. So these 2 functions are acting one after the other. So it's as good as saying f2 of f1 of x. Okay, this means that the functions are composing. Okay. Now x is a function. I can think of g as another function which goes from the set to another set, new, let's say some new set. Okay, so this is a um, so this is a this is a second function. So g of x is a shorthand to say another random variable. So g is a function, x is a random variable. So g of x is another random variable, which just means it's another function. Okay, this composed function is another function. What is its input? Its input is still an outcome or event in the sample space. Its output is its output is still a new bunch of numbers. So it's still a random variable. So it's called just a derived random variable. For this guy, the expectation of g of x, okay, it turns out that if I want to find the expectation of this random variable, I haven't even told you what the derived probability law for this random variable is. But you don't really have to figure out the probability law. What you can do is you can just do this, still do this. You can do a summation over x, which is the values that the original random variable, the capital X random variable is taking, times g of little x times p of x takes a value little x. So if you know this law, and of course all the values that that random variable is taking, you can just change this. In the previous definition of the expectation, you can just change this from x to g of x, and you can compute the expectation. Okay. You can also do since I told you that this is also a random variable, you can find its derived probability law and just take the take this type of summation as well. But this is just another way to look at it. Okay, that was the first point. The second point is that is a simple point, but just like this function x, if g, let's say the g function in particular is a square function, then instead of using additional notation, I would just use x squared to represent another. It's like a composed function. The original random variable got squared. Okay, now if you want to take the expectation of this guy is not equal to the expectation of x square. Okay, these two are different. So this is a composed function. So this is a new random variable. Expectation of x is already the expectation of the random variable x. So it's some number. It's already the property, and you're squaring it. Whereas here you have a new random variable whose expectation you need to take. Okay, so these two are different. And I guess the third property I just want to quickly say is that the expectation of I have this random function, or sorry, random variable x, which is just a function, right? So if I multiply that function with a number, so let's say I do 10 times x, and I add 3. Okay, so this is so my x was taking every outcome and giving me a number, right? So whatever number it was giving, I'm going to multiply it with 10 and add 3. Okay, that's essentially what is going to happen here, because this is also a new function, right? Therefore, a new random variable. The expectation of this guy, turns out this is just equal to, this we can just see from here, is equal to sum over x of 10 times x plus 3 times p of x is equal to x, right? I'm just gonna rewrite this over here. So this is equal to sum over x of 10 times x times p of x is equal to x plus 3 times sum over x p of x is equal to little x. Okay, capital X is equal to little x. Now this summation is equal to 1. Okay, and this summation is nothing but expectation of x. So therefore, this guy number 3 here, expectation of 10x plus 3 is nothing but 10 times the expectation of x plus 3. Okay, so this means that so in a little bit more formal I guess terminology, this property is called linearity property of the expectation, which means that the expectation is a linear operator, or it's also a function, because it's also taking as an input something. In this case, it's going to take as input the probability law and output a number. So it's a linear operator. Okay, that's all for this video. Thank you for watching.